I'm Matthew Sandoval, and this is Lab 3 Circuits. The parts of this lab are the introduction, experiment and models, discussions and questions, and conclusions. There's no code in this lab. The purpose of this lab is using the correct principles of energy conservation and current conservation to predict the behavior of circuits containing resistors in series and parallel, use multimeters to measure the actual values of conventional current and potential difference in the circuits, and examine the behavior of resistors and capacitors. The fundamental principles used in this lab are the loop rule, the node rule, and Ohm's law. The loop rule states that following the conservation of energy, the sum of all electric and potential differences around the loop is zero. The node rule states that following the conservation of charge, current flowing into a node must equal the current flowing out of said node. Ohm's law states that current through a conductor is proportional to the voltage across 2 points. The formulas provided correspond with each physical principle and will be used throughout the lab. The bottom right of this slide shows a brief preview of the results, including important values and the application of certain fundamental physical principles. This experiment had two main parts, a DC circuit and RC circuit. The models of each circuit are shown below with the images of how they were set up. In both parts of the experiment, the system will be the circuits and the surroundings will be everything else. I've included images of the physical circuits that were built. As for the initial conditions, the instructions of the lab asked us to predict the currents I1 and I2 that would be measured by the two ammeters. The calculation is shown below, and it utilizes Ohm's law. We also had to assume for this lab that all equipment was functioning properly and that wires and some other equipment have no resistance. For the discussion and for each part of the experiment, I will explain my lab procedure and my answers to the qualitative and quantitative questions in the lab doc. I'll begin with the DC circuit. First, assemble the circuit. After connecting both the ammeters, L1 read 0.01 amps and L2 read 0.01 amps, which added to 0.02 amps, which matched the initial condition prediction. After reversing one of the ammeters, it read negative 0.01 amps. This is no change. The negative sign is only due to a directional change. Next, I converted one of the ammeters to a voltmeter. I connected the voltmeter to a circuit where the ammeter formerly was, and after reading the voltmeter, it read negative 3 volts. The ammeter read plus 0.02 microamps. Notice the magnitude change. The reason for this is because the voltmeter itself has a high resistance, therefore the current will be affected. The voltmeter was then removed from the circuit, and I used it to measure the potential difference across each component. Across the 47 ohm resistor was negative 0.9 volts, across the 100 ohm resistor was negative 0.9 volts, and across the wires was 0 volts, although this was an assumption that we made. The voltmeter is also used to record the value of the current through the total circuit, which was 3 volts. After taking the magnitude of the potential difference for each component and summing it, I get 2.8 volts. The sum should theoretically be 3 volts, as we measured earlier, but the reason the sum was 0.2 volts lower than the total current is most likely due to the presence of one, the ammeter in the circuit, as well as the wires. We assume that these have zero resistance, but in reality they actually have a small amount. The images below show the round trip graph of the voltage of this circuit. You can see the voltage begins at 0, spikes up whenever both batteries are connected, then remains constant until it reaches each component where the voltage is lowered little by little until it returns to 0. This satisfies the loop and node rules. Voltmeters also have high resistance compared to the ammeter's low resistance. So when I attach a voltmeter across a 100 ohm resistor, it will have a higher resistance than the ohm resistor. The ammeter's reading will not change and will stay 0.01 amps. When the voltmeter is replaced with an ammeter, which has less resistance in parallel with the ohm resistor, the current through the other ammeter reads 0.05 amps. This can be explained because when both devices are ammeters, there is less resistance in the series. This allows more current to flow through each ammeter. Using the load rules, 3 volts minus I times 47 ohms equals 0. So the current should be anywhere from 0.05 amps to 0.06 amps as measured. The reason I calculated the current using the 47 ohm resistor and not the combination of the 4700 ohm resistor is because the low resistance of the ammeter will negate the use of the path with the 100 ohm resistor. The final question related to the DC circuit asked us to calculate the resistance of each of the following circuit elements. The measured resistance values align very closely to what the predicted resistance values were. Now for the second circuit of the experiment, I observed the behavior of the capacitor charging. After connecting a 10 ohm bulb and a capacitor in a series, I noticed the bulb brightness decreases as the capacitor charges and the bulb brightness decreases as the capacitor discharges. I repeated the procedure using a 20 ohm bulb and the results were the same. I used the physical stopwatch in order to measure the times of the 10 ohm and 20 ohm bulb charging and discharging. The 20 ohm charging and discharging was quicker. The final phase of the RC circuit was to solve for the RC time constant. To solve for the time constant, you multiply the resistance of the bulb, the farads of the capacitor, which means that one time constant for the 10 ohm bulb should take 10 seconds, and for the 20 ohm bulb should take 20 seconds. These values, however, differed from the actual charging and discharging times related to the bulb. The reason for this is because 5 times the RC constant typically represents the time at which a capacitor is considered fully charged or discharged in RC circuit. So if you multiply the time constant for the 10 ohm bulb by 5t, you get 50 seconds, which match the recorded charging and discharging times. 20 ohm bulb, 5t should equal 100 seconds. This does not really match the recorded charging and discharging times, but it closely matches the one time constant time, which must mean that the capacitor did not fully charge in my case. The values of voltage, amperage, and their other relevant calculations either matched or were extremely similar to predicted values. Possible sources of error include human error in handling circuits, measuring time intervals, using equipment, possible faulty equipment, possible use of circuit pieces with incorrect values, errors in calculations, and incorrect interpretation of values and instructions for the lab, What if I charge the capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? In an ideal model, a capacitor charging with no resistor would reach full charge almost instantly, since the time constant, t, would be 0. Using an ammeter to measure this in real life, the capacitors seem to take anywhere from around 1 to 2 seconds to charge. The measured time differs from the predicted time due to the small amounts of resistance in the battery, ammeter, and capacitor.